Okay, so why do conductors conduct? You should be aware by now, but conductors conduct because they have free moving electrons. So generally, the structure of conductors means that they've got sort of full energy levels, and then the very outer energy level has just one or two electrons in it. And we know that energy levels have spaces for the electrons to move, so that electron can easily be either separated from the atom and start moving around the structure, or it can move around in the atom itself. So current can flow when the electrons are free to move. In conductors, electrons are free to move. In perfect insulators, electrons are not free to move. And to understand why, we need to look at the structure of atoms. So electrons are in energy levels or energy shells, which can hold a certain number of electrons. So that's why they don't all just crowd in the smallest electron. The first one can only hold 2, then 8, and etc., etc. These levels can be empty, partially filled, or full, but no electron can be between levels. If a level becomes full, the electrons become tightly bound to the nucleus and are very unlikely to move. In perfect insulators, the outer energy level is full, and the outer energy level is the valence, called the valence level. So electrons don't move because they're tightly bound because it's a full energy level. But in conductors, there are fewer electrons in the outer energy level. These are not tightly bound, so can move away from the nucleus easily. In copper, there's one electron in the valence shell, which becomes free to move. It can therefore drift to neighbouring atoms, which is what causes the electric current to flow through it. So when we look at atoms, we tend to look at a lot of atoms together. So this is just a single atom with energy shells. What we see is we see lots of atoms together, and we sort of combine all of these shells, and we call them an energy band. We group them together in a band. We call it an energy band. So it's basically just lots and lots of the same atom, and we look at them in bands rather than energy levels per atom. So we saw for lots of the structure of single atoms in which the electrons occupy discrete energy levels. When atoms are close to each other, the free moving electrons can use the energy levels of their neighbours, and the energy levels become grouped together in a band, and we call this an energy band. A band is said to be occupied if there are electrons in it. And just like energy levels, these bands can be full, partially full, or empty, and no electron can be in the space between the bands, and that's called the band gap. And the band gap is very important when looking at whether or not a material will conduct. It's not possible for an electron to exist with an energy level that would place it in the band gap. So the highest energy level, the highest energy band, which is the most outer occupied band, is called the valence band. So the one that's sort of here, the highest full energy band is called the valence band. The first unfilled band is called the conduction band. So here. The conduction band can have 1 or 2 electrons in it, but if it's full, it's the highest full energy level is the valence band, and the first unfilled band above this is the conduction band. And for a material to be able to conduct electricity, it must have electrons in its conduction bands or spaces in its valence band so the electrons can move within the valence band. So here is an example of band diagrams for an insulator and a conductor. So in an insulator, the valence band is absolutely full and there's nothing in the conduction band at all. So it requires an awful lot of energy to overcome this gap here and for electrons to jump up into the conduction band. So this is why this gap is huge, because it's basically representative of the amount of energy required to release an electron from that valence band when they're nice and tightly held there to jump up to the conduction band. Alternatively, in a conductor, we can see there's basically overlapping because the valence band, it takes hardly any energy at all for electrons to jump up into the conduction band because they already exist in the conduction band. So we have like an overlap between the valence band and the conduction band because it doesn't require the energy to overcome, and it doesn't need to overcome any gap because already there are electrons in the conduction band. So in a perfect insulator, the valence band is full and the conduction band is empty. This gap between the valence and the conduction band is large, and at room temperature there's not enough energy available to move electrons from the valence to the conduction band, where they would be able to contribute to conduction. In a conductor, some electrons already have sufficient energy to exist in the conduction band, though it's not fully occupied. This means that they can move throughout the material and it therefore can conduct. The conduction band overlaps with the valence band, making it easy for some electrons to gain enough energy to be promoted to the conduction band, and they will then to be able to be free to move. Temperature is important when we're dealing with energy, because temperature, you can increase the energy that the electrons have by supplying them with energy, and you can supply them with thermal energy, which is the easiest way to do that. The more thermal energy in the material, the more energy the electrons have, making them more likely to move. In insulators, the band gap is so large that it's unlikely that an electron would have enough energy to move to the conduction band. But if there is enough extra energy produced, and that it has to be a lot of energy, then insulators can be forced to conduct, and that is called the breakdown voltage. And you see examples of breakdown voltages in air when you see lightning, because air is an insulator, but lightning can pass through air. So at room temperatures, there's no conduction in a perfect insulator. Unfortunately, not all insulators are perfect, and as mentioned earlier, it's possible to give electrons in an insulator sufficient extra energy for them to conduct. But in order for this to happen, the voltage must be very, very, very large. And that's why air can be forced to conduct if there's a big enough voltage, if there's enough energy given, but it has to be a lot of energy. So that's why obviously lightning is a big there's a big amount of energy, there's a big amount of potential difference in a lightning. Applications of conductors and insulators. Obviously, power cables have conductors and insulators together. Conductor allows the electricity to flow through it. Insulators are usually wrapped around the conductor, so we don't protects us from getting a shock from the conductor inside. The energy involved in them is very high, so it's important that they are well insulated. It's also essential that they're good conductors because they transfer electrical energy over a long distance. They also need to be light, and for this reason copper is rarely used, and instead thin strands of aluminium are used with some strands of steel for strength. Aluminium is light and a good conductor, and the use of thin strands instead of thick single cables helps with the skin effect. So you don't really need to know about the skin effect, but basically as the frequency get higher, the layer where the most of the current flows get thinner, so the effective resistance of the material gets higher, and you don't really want that to happen. But don't worry about that too much. That's not really higher physics. Okay, semiconductors. They're in between conductors and insulators. So semiconductors, they have sort of a half-filled outer energy level. And usually at room temperature with normal semiconductors, there's still a gap. It's still difficult to get them to conduct because they're in a relatively stable structure there. So the electrons don't really want to move from there. But if you do add some external energy, so light or heat, they can be made to conduct relatively straightforward in a relatively straightforward way. So whereas insulators, they have to have a huge amount of energy for anything to happen. Semiconductors only require a small amount of energy to promote the electrons and to allow the electrons to move. Or, you'll see later, you can also introduce impurity atoms that will allow the semiconductors to conduct. And obviously, so the semiconductors have a smaller band gap. It's much smaller than the insulator. Obviously, it's not the same as a conductor. There's not overlapping. There is still a band gap, so you still do need some energy to allow it to conduct because a semiconductor doesn't conduct in room temperature, but it is relatively easy to allow them to conduct if you add a stimulus such as heat or light, so like light-dependent resistors. So most commonly used material is silicon. Pure silicon has a high resistance, but it can be made to become a conductor more easily than an insulator. Applications of semiconductors, temperature-dependent resistors and light-dependent resistors, so thermistors or LDRs. And basically, we know that temperature-dependent resistors and light-dependent resistors, temperature up, resistance down, light up, resistance down. So basically what's happening there is if you increase the temperature, you're giving some of the electrons extra energy, in this case thermal energy. So they've got more energy so they can overcome the band gap and occupy the conduction band and therefore start conducting. And again, with light, if you supply light energy, you're giving the electrons extra energy so they can overcome the band gap and start to conduct. So in summary, conductors, materials with many free electrons. These electrons can easily be made to flow through the material. So metals, semi-metals like graphite. Insulators, these are materials that have very few free electrons, so plastic, glass and wood, very, very difficult to get them to conduct. Semiconductors, they lie between the extremes of good conductors and good insulators. They are crystalline materials that are insulators when pure, but will conduct when an impurity is added or in response to light or heat or a voltage being added. And these are some examples of semiconductors.